Once all that's done, we can get to the results, and for that we'll cut to the regression table. But seriously, don't worry, I'm going to explain it. I'm looking here at table 1 on page 427. The title of this table is Risk of Armed Conflict by Neo-Malthusian Population Pressure Variables. You'll remember that risk of armed conflict is our dependent variable, so for all of this table it's explaining the risk of armed conflict. On the left hand side we have the explanatory variables. These are our independent variables. So if we're testing to see if the risk of armed conflict depends on those independent variables, population growth, population density and so on. The first variables are the ones we are genuinely interested in for the sake of the hypothesis, which you'll remember was countries with high population growth are more likely to experience domestic armed conflict than countries with low population growth. So we've got population growth right at the top there. But the thing with building models is that a relationship is never as simple as one thing leading to another. Your height is not just a simple function of your age. Lots of other independent variables need to be considered, such as exercise, smoking, fruit consumption and so on. The same is true of the risk of armed conflict. We can't just look at population growth, we need to look at other factors too. These are our control variables like total population, GDP per capita and so on. We're not actually interested in those control variables, but sometimes we put them in and they turn out to be statistically significant. In some instances we put them in and not only are they significant, but they take away significance from the main independent variables we're interested in. If they do that, then we need to find against the hypothesis. Across the top of the table, you see we've got 6 different models. The trick with this kind of modelling is to run several different versions of the model, each with a different combination of variables in it. By doing this, we can find out which variables stay significant across models and which ones become insignificant. But how do we know which ones are significant? Well, if we look at the table, we find that it's full of stars. Some statistical purists don't like the stars, but they really do make life easier. At a glance, we can see the significant variables. But how significant? We'll come to that in a moment. First, let's look at the numbers. For every variable and every model, we have a pair of numbers. Let's look at population density in model 1. The first number is minus 0.088. The first number is what we call the coefficient. What it means is this: if I change the independent variable, in this case population density, by 1, how much will my dependent variable, risk of conflict, change by? Well, the answer is that the risk of armed conflict will change by minus 0.08. For every 1 I add to population density, risk of conflict goes down because it's minus by 0.088. Again, add 1 to population density, conflict goes down by 0.088. The number underneath is the standard error. I think of it as the give or take in most instances number for the coefficient. So if I add 1 to population density, then the risk of armed conflict goes down by 0.088, give or take 0.053 in most cases. Now, we want that standard error to be less than half of the coefficient in order for us to have a good level of probability, but here we don't, which is why it only gets 1 star. The levels of probability are explained at the bottom of the table. 1 star means probability is less than 0.1, 2 means less than 0.05, and 3 means less than 0.01. But the probability of what? Well, that the effect of the probability the effect on the dependent variable is occurring not because of the independent variable, because of random chance. So for population density with a p of less than 0.1, we would expect up to 10 times in every 100 the effect of the risk of armed conflict would be by random chance, not by population density. If I look to model 2, I see there's no stars for population density. No significant relationship in this model between population density and risk of armed conflict. But when I move to model 3, I see we have 3 stars. For every time I increase population density by 1 in model 3, I decrease the risk of armed conflict by 0.156, give or take 0.052. As we've got 3 asterisks, p is less than 0.1, means that the chances of it being random occurrence are less than 1 in 100. But model 2 said there was no relationship. What's the difference between the models? One has infant mortality in it. Infant mortality was included as a control in model 2, but not in model 3. This suggests it's not really population density that's doing the work here, but infant mortality rate. And that's what we do with modelling. We put different variables in and pull them out and see which ones have statistical significance most consistently. In this case, population density is not consistently significant, but infant mortality is. So if you want a variable that gives an indication of the risk of armed conflict, don't look to population density, but look to infant mortality. A few other factors should be considered. The first is the N. That's nice and simple. It's the number of cases. You remember in this paper the unit of analysis is country year, so model 1 has 7752 country years or country year observations to look at. The number varies across the models because for some models we don't have information for every variable. Or as in model 2, the model's been deliberately restricted just to include recognised states. As such, the other cases have been missed out. The constant is also known as the intercept. It means what would we estimate the dependent variable to be if we set all of the independent variables in the model to 0. In isolation it doesn't tell us very much, but it's there anyway. We'll skip the log likelihood and jump on down to the last item, the Pseudo-R Squared. The Pseudo-R Squared takes a value between 0 and 1 and tells us how powerful our model is. It basically says how much of the variance in the dependent variable is explained by the independent variables we've used. If we get an R squared of 0, then none of the variance is explained. Our independent variables do nothing to explain our dependent variables and our model is useless. If we get 1, then all of the variance is explained. Our selection of independent variables gives a perfect model with which we can understand our dependent variable in its entirety. Everything is explained. In the social sciences, we seldom get an R squared that's anywhere near 1, as there are just so many things that we don't know and can't model. But the pseudo-R squared can be useful to compare between our models. The ones with the higher number tend to be better able to explain variance in our dependent variable. But frankly, in these models, the pseudo-R squared comes out so close to 0.1 in all of them that I'd be reluctant to interpret much into it.